Hello and welcome to Podcast.init, the podcast about Python and the people who make it great. I would like to thank everyone who has donated to the show. Your contributions help us make the show sustainable. When you're ready to launch your next project, you'll need somewhere to deploy it, so you should check out Linode at linode.com/podcastinit and get a $20 credit to try out their fast and reliable Linux virtual servers for running your app or trying out something you hear about on the show. You can visit the site at www.podcastinit.com to subscribe to the show, sign up for the newsletter, read the show notes, and get in touch. And to help other people find the show, you can leave a review on iTunes or Google Play Music, tell your friends and coworkers, and share it on social media. Your host as usual is Tobias Macey, and today I'm interviewing Ryan May, Sean Arms, and John Leeman about MetPy, a collection of tools and notebooks for analyzing meteorological data in Python. So could you each introduce yourselves? And we'll go in the same order that I mentioned. So Ryan, if you could go first.
Hi, my name is Ryan May, and I'm a software engineer at Unidata.
Hi, my name is Sean Arms, and I too am a software engineer at Unidata.
And I'm John Leeman. I make 3 software engineers at Unidata.
And how did you get introduced to Python, if we can go in the same order?
So I've been using Python since around, I believe it was 2006. I've been a MATLAB user up to that point. So my background's in electrical engineering and radar meteorology, and MATLAB's used extensively there. And I'd started down that path and then heard about a lot of, maybe not rumblings, but a lot of things about how Python had these uses for scientific stuff. So I started poking around at it and used it one day to I was trying to debug some of my research code, and I dumped out arrays from GDB. So you can actually just dump out memory values from the GNU debugger. And so I did that and used Python to plot up the values and managed to find many bugs, including some I wasn't expecting to find within my code. And that kind of sold me on how easy it was to get the plotting going. And even trying to load that data into MATLAB would have been a pain. So that's kind of where I started. And then that summer, I was supposed to be studying for my PhD qualifying exam, and instead I spent lots of time learning Python. And then in the fall, I applied it to some classwork, and I haven't looked back since.
And Sean, how did you get introduced to Python?
Yeah, so it would have been that fall when Ryan started using it in his coursework. We were taking a course called Objective Analysis, and I decided that would be a great time to learn C. And I was blowing my array bounds all over the place. It was disgusting, coming from Fortran, which is what we were taught as undergraduates. And I think the final straw down that path of let's learn C was when the instructor told us to plot up some of the values from the objective analysis routines we were doing. And it involved compiling a Fortran-based image package and using Fortran to plot it up. And Ryan looked at me and he said, dude, no, just don't. And he sent me a little script doing some basic plotting. And from there, I think pretty much every morning for the next, 2007 to 2011, when I moved to Boulder to work at Unidata, I was in his office for hours discussing Python stuff and plotting how to take over the world using Python. So
I should probably clarify that Sean and I both went to the University of Oklahoma for our undergraduate and graduate degrees in meteorology.
And John, how about you? How did you get introduced to Python?
Well, so I actually went to the University of Oklahoma as well for my undergraduate degree in meteorology. And then I moved up to Penn State to do my graduate work in geoscience in general. But I started using Python in, I would say, about 2008, so a little bit after these guys. And my background has been mostly in experimental geoscience and geophysics. So I needed a way to make plots and data visualizations of experimental data from complex new apparatus that there weren't toolkits for. So I needed to learn some way to do that, and actually bumped into Ryan around that time, and he introduced me to Python as well. I've used it all throughout my graduate work, and then now here full-time at Unidata.
And if you could do a brief diversion about what it is that you do at Unidata, because since you all work there.
Sure. So Unidata, we're part of the University Corporation for Atmospheric Research. That organization is responsible for managing the National Center for Atmospheric Research, which is a federally funded research and development center that does research on the atmospheric sciences. And then UCAR also has this community programs division, of which Unidata is one of them. And so our focus is to produce technologies for working with weather data and distribute weather data, and generally help the academic atmospheric science community be able to integrate weather data into their education and research goals.
And is MetPy part of that?
So MetPy is a recent development on that side. Python, we've I'll mention how long we've been using it for a while. It's really seen an uptake in use in the meteorology and atmospheric science communities within the last, seriously, in the 5 or 6 years. I think we had a symposium started, our big American Meteorological Society annual meeting has had a Python symposium. I think this year was the seventh or eighth that they've had. And so that started then, but the real uptake, I'd say, in the last 5 years has really seen, everyone within the community we interact with has expressed an interest in using and learning Python. And so Unidata, being responsive to our community, has started to invest much more in trying to meet the needs of people wanting to use Python. And so we do a lot of, both in terms of developing software tools like MetPy, and there's another package we work on called Siphon that's used to download remote data. And then we also do a lot of training in terms of workshops, as well as trying to produce online training materials like the notebooks you mentioned.
And so if you could dig a bit further into what MetPy is and what the problem that you were faced with when you first started it.
Sure. So MetPy is a collection of tools in general for working with weather data. So that goes from reading in data, which we in the atmospheric sciences have a wide variety of archaic formats of data for different types of data. So in meteorology, we work with surface-based instruments. You have a temperature and humidity sensor out somewhere to take measurements, as well as wind. We also launch weather balloons to try and gather information about what's going on in the upper levels of the atmosphere. There's satellite-based sensing. There's radar. So that's more about detecting precipitation and severe weather like hail or tornadoes. And there are many others I'm sure I'm forgetting right now, but those are the big ones. And so we have a wide array of formats for all those different sensors. And so the code to read in that data can be a little tricky. And so MetPy is trying to bring those different formats to the Python world. I will say at Unidata, we've worked to develop kind of a general format called NetCDF that tries to make it easy to have a more self-describing data format as opposed to some of these binary formats where if you don't know what the format is, the data's lost. So beyond data formats, MetPy is also about having a library of calculations, reusable calculations to try to apply to these data files that you read in. So if you read in some temperature and humidity and you want to calculate the dew point, or you can go from that maybe wind chill with the wind data or heat index or a variety of other different parameters that meteorologists would be interested in. And so trying to come up with a library of those that are reusable, both for observational data as well as things that come out of numerical prediction models. And then the last part of MetPy is providing some utilities for generating plots. So we have our domain-specific plots that we're used to looking at, both for looking at, say, we have these we call soundings, SQT diagrams that we use for plotting balloon data, or we also have things for looking at the surface station data, and just a variety of other little odds and ends that the meteorology users are used to looking at. And so just trying to make reusable tools for that, and kind of in the vein of trying to plug into the rest of that scientific Python stack. So Matplotlib exists, NumPy, SciPy, all these great tools exist that provide arrays or numerical algorithms, or for Matplotlib, the publication quality graphics. And so one of the things that MetPy tries to do, as opposed to some other Python libraries that exist out there, is to just plug into the stack that's already well supported, being developed elsewhere, and just fill in our domain-specific part rather than reinvent the entire wheel.
Yeah, there's definitely quite an extensive suite of offerings for being able to manipulate data once you have it into a sort of standardized format. So it seems that the primary goal of MetPy is just to serve as an interface to the variegated different types of data sources that are used within meteorology and atmospheric sciences. Does that sound like an accurate synopsis?
For part of it, but part of it, it definitely comes down to the calculations. That's a big part, trying to go back to various literature references and look at the scientific literature for where some of these formulas came from, for where these calculations were doing evolved, and have a citable source for that, as well as doing robust testing of the calculations. And so historically, there have been other packages that have kind of gone along this road. One familiar to many meteorologists would be this package called GEMPAC that actually came out of the National Centers for Environmental Prediction, so one of the federal government's entities that does weather prediction. And they provided this nice tool called GEMPAC that is used for making weather maps and various analyses. And that worked great in the 80s and 90s, but as we get towards modern times, it's showing its age, and development has kind of, as other software packages advance, development of that has kind of been ceased. And so you have this base functionality of having this library of calculations, but those were all in C and Fortran and difficult to reuse. So one of the things MetPy is focused on is providing a reusable set that no matter what your problem is, if you can get your data into a NumPy array, you can apply the calculations we have within MetPy.
Yeah, and that's really a big part of it. The NumPy array is such a backbone of scientific analysis that as long as we can keep mileage out of it, for example, like Ryan mentioned, you've got your dew point, you've got your temperature, you want relative humidity, you can do a simple calculation that way. But in meteorology, I mean, part of the problem we have is we're on this rotating sphere, and when you're wanting to do spatial derivatives and things like that, all of a sudden coordinate systems start playing a big role. And so that's one of the challenges with MetPy is being able to do, even on paper, what would be a simple calculation, but being able to do that smartly, and I don't want to say in a black box way, but making sure all the information, for example, about the coordinate system is there with the data as well, so that you can do those calculations correctly.
Yeah, definitely. And I think another part of it too is, we're working with real data a lot of the time. We're trying to do these calculations, like calculate how much potential energy there is in the atmosphere from a balloon sounding that might have a sparse sampling of the atmosphere in some point. So there might be missing data, or the balloon might have popped early. So we have to make sure that our calculations are robust and are able to deal with these complications that we get when we're taking real measurements.
I should also add that in addition to the NumPy array, there's one other thing we do readily depend upon in terms of doing these calculations, and that's a library called Pint, which implements physical quantity or unit support. So, for instance, you could take a NumPy array and say, okay, this array of temperatures is in degrees Fahrenheit, or it's in Kelvin, or maybe this array of lengths is in meters and not kilometers. And so that was kind of when we started this, one of the founding principles was to try and make unit support built in so that, in my experience, I'd spent a lot of time trying to run down errors in my code. And I don't think any of them turned out to be unit things, but you spend a lot of time just making sure, am I using all the units correctly in these various places? And by using another library to let the computer track the units rather than making the programmer do it. And all the horror stories of various things that have gone horribly wrong when units were incorrect, like the Mars Express. Was it the Mars Reconnaissance Orbiter? No, that's the one that worked. There was another Mars probe that never entered orbit around Mars because of unit issues, it was determined. So that kind of hammers home the importance of making sure those are correct and trying to let the computer do it rather than the programmer. And so that we have NumPy arrays and then just ask people to attach units to that, and then the code can work correctly. And that's really important with all the, you can't do things in degrees Fahrenheit when you're doing physical calculations. You need to use Kelvin. And there are various other things where initially we didn't have that, and a lot of documentation in MetPy was spent just saying this parameters in this unit, this parameters in that unit, and it really simplified the documentation to allow the computer to just track the units for you and do the right thing.
Yeah, units are definitely a significantly important piece when you're dealing with, physical measurements and data that comes from that. And in one of the other interviews that I did with the folks from AstroPy, they mentioned that they have a unit library embedded within their project as well. And so when I was speaking with them, I was thinking to myself how it would be useful if that had been extracted to be used in a standalone fashion. And then when I was reading through your documentation and saw the reference to the Pint library, I was thinking how it's fortunate that exists as well, so that there is that capability of incorporating unit support into other libraries as well, because of the fact of how ubiquitous it is when you're dealing with actual physical sciences and physical units of measure.
Yeah, absolutely. The one unfortunate part, though, is that so many attempts on these physical quantity or unit packages have been attempted. So off the top of my head, I can think of AstroPy units, Pint, quantities is another one. And those are just the ones that I know are well supported or have used in the past. And I remember seeing a talk at SciPy years ago, say 2013, that actually benchmarked, I think, about 10 of these different unit packages. And so one unfortunate part is that it's been redone so many times because no one gets enough mindshare, and the fact that it's difficult sometimes to integrate these things together. So one of the challenges we face, as Sean alluded to with the spatial derivatives, is one thing we'd like to make more use of within MetPy is the X-array library, because that has a notion of having these arrays with coordinate system, or at least the coordinates on which a grid of data is available, would simplify doing things like spatial derivatives or integration and things like that. Those do not readily play with the Pint unit package. And so, there's some more work that needs to be done to try and make these two play together nicely, but that's probably one of the challenges that, the base NumPy array doesn't have a notion of how to do physical quantities. And, I think that's probably one of the problems that, from my perspective, we most face in the Python scientific stack, because I keep seeing this question pop up over and over across various issue trackers on GitHub, is the question of, oh, this doesn't play well with this unit package. How do we solve that?
And as you were describing some of the problems of manipulating and analyzing some of the data that you're dealing with, I was thinking about how it seems that because of the fact that atmospheric data is necessarily an open system as opposed to a lot of the more controlled experiments that are done with some of the other physical sciences such as physics or chemistry, it seems that there's a much greater difficulty in being able to run the analyses on the information that you do have because of the inherent uncertainty. So I'm wondering if you can discuss a bit about the differences between meteorological and atmospheric sciences and some of the other physical sciences, and then also maybe speak to how you deal with some of that uncertainty when you are analyzing the data.
Well, certainly when you're dealing with observational data, inherently it's noisy. And so doing some things like taking derivatives of observational data is fraught with problems because you're doing a subtraction and that ends up having, blowing up under the uncertainty in the data. So, and one of the big differences between meteorology, atmospheric sciences, and other sciences, as you alluded to, was you don't have a laboratory. The only laboratory we really have, minus a few small-scale tabletop experiments, is you have the world. And so all you can do is take observations, by and large, as far as, actually traditional laboratory type things. And so that's kind of you end up with doing a lot of case studies. You go back and look at a lot of data, but you don't have an opportunity to really have a control experiment and go run the same experiment with different conditions and see what happens. Instead, a lot of what we rely on is these numerical models, either for prediction purposes, so your daily weather forecast, the tool the National Weather Service forecasters look at, or your private sector forecasters look at, is output from a numerical prediction model. And that gives you data on a nice even grid. And then the same thing happens for researchers. You can take maybe it's based on a real case, maybe it's just a synthetic set of conditions, but you can apply that same numerical modeling technique to some chosen set of initial conditions and see what evolves in the computer. And, there's some ties between what goes on in the computer and what happens in the real world, but there's some differences. One of the big challenges you face, though, is a lot of tools work really well for model output because you have that fixed grid. Things aren't as noisy. It's well-arranged data, and, you don't have missing values. Whereas real data, you have data dropouts, you have things on irregularly spaced samplings, you've got the uncertainty you mentioned.
You got instrument failures. You have all kinds of weird things that can get injected into the real data.
And as you mentioned, a lot of the sort of visibility that people have into the discipline of meteorology is via their local weather forecasts. So can you talk a bit about some of the sort of research and experimentation that goes on that's not necessarily consumer-facing?
Sure. Well, it's always a never-ending story of trying to better incorporate the real atmosphere, the actual physics that are going on into a forecast. And so those numerical prediction models that I talked about, what you're doing is meteorology was once summed up to me as a lifetime of challenges in one word: air acts as a fluid. So meteorology is applied fluid dynamics. And so that's a large sort of the problem. And then you take that and you add one more problem of thermodynamics. So you have water vapor in the atmosphere, and that condenses into liquid and gives off an incredible amount of energy. And so that's what gives rise to storm clouds and precipitation in general. And so take those two together, and there's no end of challenges to try to simulate that within a computer. And so what you have in these numerical prediction models are you take these equations that describe how this air fluid moves across the globe, and the globe is spinning, it's not stationary. And so you've got Coriolis effects to deal with there. You also have, as a fluid, you've got viscosity to deal with. It's a compressible fluid, so air pressure matters and density changes. And so you take those equations, you put them on a grid, and then you run them forward, essentially. You take a set of conditions and move forward. And so that alone has all sorts of challenges depending on how fine a grid's, the spacing of your grid points are. That affects how accurate your forecast can be. It also affects what size of things you can capture within there. And so you can often get broad scale weather patterns right, but trying to get, I think nominally a lot of the models we're running right now is on a 3 kilometer space grid, and those are actually probably the higher resolution ones. If a storm is 100 kilometers across, you've got 30 points, which seems like a lot, but that's only now getting to that point, and it's still not a great, if you're trying to predict a tornado, that's still not enough to try and predict a tornado well in advance. So that's part of the problem. And then the other problem is we have these noisy observations with errors and things. And so trying to inject those into that numerical prediction model is a challenge. And what you actually end up doing is you start with the output from the numerical model, the previous output, and then you adjust it based on what the observations actually say. And you've got a lot of statistics and math, and it's called data assimilation. You're assimilating actual observations or data into the forecast. You actually can't start from scratch because we don't have enough of the observations of all the things. You have wind, that's good, but detailed information about what precipitation is going on. And that's actually one of the problems I glossed over there is we talked about all these 3-kilometer scale and how the fluid works, but there are some processes you can't simulate, like the air rises and condenses water vapor into little droplets in the air. And you do enough of that, and then those little droplets begin colliding together and coalescing into bigger raindrops, and eventually you get rain, or at least that's one simplified explanation of it. You can imagine you can't simulate every raindrop within a numerical model, and so you've got to make some we call microphysics parameterization. You've got to basically kind of come up with a formula that makes approximately correct results come out from a 3-kilometer grid that says there's this many raindrops here and there's this much water vapor present, and this is kind of what's prone to happen.
I mean, to properly model the atmosphere, we're talking motions on the scale of millimeters up to thousands and thousands of kilometers. And so you've got to chunk up the problem into these parameterization schemes or these simple, almost like cartoon-like drawings where you're trying to represent the processes on a smaller scale in a bulk way that kind of fits in between your grid points of the model you're running. So there's a lot of observational work that goes into coming up with these parameterized modules that the models use. But of course, those schemes may have been developed for a model that was running at 60 kilometers, and now we're trying to run the model at 3 kilometers, but we're using the same parameterization schemes that were made for a model running at a much larger grid spacing. And it's pretty clear that you shouldn't be doing that, but it's not clear where to move forward from there. So you get a lot of errors introduced by doing that.
And there's a lot of complex couplings too. I mean, we haven't talked about, atmosphere, ocean, or the biosphere, cryosphere. There are all these other systems. Everything's tied together, right? If a volcano erupts, it's going to inject massive amounts of CO2 into the atmosphere and ashes. There's no way you're going to capture that in a model, much less all of the other complex interactions that occur with things like tropical storms. So you have to really consider the entire Earth system, and that's something that we're just not quite up to the task of doing.
And that's where you were asking originally about where areas of research on this. So data assimilation and better ways to incorporate new data sources into a model where this data assimilation, you're kind of taking observed variables and trying to back out primitive things. So you're looking at how much precipitation fell over top of this area and trying to back out what the conditions were, how many raindrops were distributed in a 3D volume over that area. Or you're trying to take a satellite observed profile of atmospheric temperature with height and trying to say, okay, this is what the satellite saw, what might really be going on here. So that's just data assimilation and trying to come up with better statistical techniques to fit that. You've got the parameterizations we mentioned, trying to come up with better ways to handle different scales and just more accurately do things. We just talked about raindrops. There's snowflakes, there's hail, there's different tendencies for how the water vapor is going to condense depending whether over the ocean or whether you're over your land. The availability of condensation nuclei, as we call them, and so there's problems like that.
And each one of those categories has its own set of problems. So if you're looking at ice crystals, how does water vapor condense onto a real sharp and pointy looking ice crystal as opposed to something that's nice and symmetrical? And it's almost intractable when you look at it.
There's a really good example of that where here in Colorado we get snow a lot, and noticing the other day driving in from home into work, we encountered about 3 different kinds of snow. You got little pellets, you've got flakes, you've got these big clumps of flakes that we call aggregates. What you're getting there depends highly on what the temperature is, how much water vapor is in the atmosphere, and not just what the temperature is, but what the temperature profile is from the ground to up in the upper parts of the cloud where the snow is actually forming. And so very small changes in that temperature and humidity can affect what you're getting at the ground. Might be a minor detail until you think about how that impacts how much your snow depth is going to be. So your forecast of, is it 5 inches? Is it 7 inches? Is it 10 inches? I mean, there's a lot of other effects that go into that, but just trying to model accurately snow depth is very dependent upon what kind of snow you're getting. Our rule is 10 inches of snow ends up melting to about 1 inch of liquid water. That's a rough rule of thumb, but that can actually be anywhere from 5 inches of snow to 1 inch of liquid. to 30 inches of snow to 1 inch of liquid in extremely dry, fluffy cases. And that has profound effects for, say, flood forecasting or other hydrological applications. So there's a lot of devil in the details there.
Yeah, and each of these complications that we've talked about, be it hydrology or snowflakes, there's an entire research community that works on each of these problems.
Yes.
And there are an incredible amount of people that go into making these numerical models do what they do.
I don't even know what to say to that. As you mentioned, there's just so much inherent complexity in everything that is entailed with dealing with the atmosphere and the global climate because of the vastness of the system and our current inability to accurately model every component of it simultaneously. We have the computational power to be able to do some localized modeling or localized approximations of the data that we have, but even just capturing the totality of the data is something that's an impractical problem. So I guess a couple of different branches of questioning from there I'd like to explore are, one is I'm curious to what degree machine learning or artificial intelligence systems are employed when dealing with climate and weather data, and also to what extent has the increase in our ability to create sensors and distributed hardware platforms contributed to the increased ability to actually collect data for climate and weather information?
I'd say both of those areas are active areas of research. So I think, again, within the last 5 years, we'll say, roughly, that's when you really started to see more papers on doing machine learning, especially in the public sector. I think there are private corporations who kind of been on the early side of that wave in terms of applying machine learning to weather data. Companies like the Climate Corporation that have a vested interest in trying to provide these useful analyses to try and help predict, say, crop yields or insurance losses and things like that. The hazards portion of meteorology is, that drives a lot. I mean, that's the thing that, we try to never lose sight of is on some of these things, people's lives end up being at stake when it comes to hurricanes and tornadoes. But there's then, people's livelihoods are at stake when it comes to hail or drought and things like that. And so there's a lot of public impacts there. But on machine learning, that's, it's going on a lot, but I think we're still in the research phases of that, minus some public or some private sector applications that I don't think are as prominently advertised. I think that's a secret sauce for a lot of companies out there. And what was the other question there?
The other question was asking about how the increased ability to create distributed sensor platforms and sensor networks has contributed to the ability to increase the amount and quality of data that we can collect about the climate systems.
I'd say the impacts haven't been realized yet. A lot of projects ongoing in terms of talking about trying to collect all these pressure measurements that are available through, I think, Android phones, or at least some versions of Android phones have had pressure sensors available on them. And so there's active projects seeking to try and grab this data and see, it's noisy data. The sensors that you get on phones are not as exact as a well-calibrated weather station, but you make up what you lose in quality there, you make up for in quantity. And so, again, applying some machine learning or some other advanced statistical technique, that those are open questions for how much can you make a benefit of. But they're definitely, we as a community are looking into trying to make more use of these distributed data sets that are available. And then you also have a lot of work going on starting to look at drones as autonomous platforms for collecting weather information. A lot of storm scale research and, bigger storm, hurricanes down to severe thunderstorms, involve, if you're trying to get information not at the ground, but at, up around what's going on at the top of the thunderstorm or, mid-levels of the thunderstorm, involve flying a plane through them and around them. And that has its challenges. There's only so much you can do with a craft that has a human pilot on board. Human pilots have limitations on how many hours they can be flying. And so you're seeing a lot more now starting to look at these autonomous platforms for trying to fly instrumentation in and around storms and trying to enhance our understanding of what's going on. We've done a lot with remote sensing through radar and, launching balloons near them, but I think the missing piece has really been trying to get what we call in situ measurements of what's going on literally inside, rather than trying to look at it from the outside.
Well, and if you can imagine too, even just instrumenting the infrastructure that we already have. So say you had a meteorology package on every semi driving the interstates every day. That's an incredibly dense spatial and temporal sampling of what's going on. So if you had a winter weather event that was happening, that's obviously a large hazard. There can be traffic accidents, impacts to getting materials back and forth, logistics, acoustics and so on. That dense sampling could really help us understand what's going on there, or at least better mitigate or respond to it as it's happening. So I think that's going to be a big thing eventually, but in terms of aggregating that data, visualizing it in some meaningful way, and being able to interpret it in an operational scenario, we're nowhere close yet.
And that actually fits within a broader problem we're already experiencing in terms of big data. That's an overused term, but we are definitely starting to feel the strain of these large data sets. We're talking about these distributed ones, which would be big, but they're still just single points. Whereas we're starting to talk about numerical weather simulations, a quarter degree resolution spanning the entire globe. So quarter degree latitude, quarter degree longitude, and then say on order 60 levels in the vertical direction. You got these three-dimensional grids. That's one operational model coming out 4 times a day, and it's doing forecasts every 3 hours out to so long, and every 6 hours out beyond that, out to 384 hours. So that's a lot of data right there. And then there's actually a new weather satellite now called GOES-16 that should be coming operational sometime this year. And that brings with it a lot of nice new capabilities, impressive sensors, higher time resolution capabilities. But the data volume coming out of that every hour is reaching volumes that Unidata historically has shipped a lot of data out to the universities. I forget what I think our aggregate bandwidth is almost 2 gigabits out to the universities, 20 terabytes a day. Sorry. Yeah, so our aggregate at 20 terabytes a day, or it's almost saturating a 2 gigabit network connection. And we're used to doing that. And now with this new satellite, we're talking about not even trying to ship it all out and just exploring solutions, hosting it here and up in the cloud, because we just aren't equipped to continue to blast out all of this information.
And not only that, one of the things we notice is that with our community of users, anytime we say, hey, would you guys like this data, whatever it is, the answer is always yes.
Meteorologists like looking at pictures. So.
Doesn't matter what it is. The answer is always going to be yes. And really, we're past the point where it's not, would you like this, but what do you want to give up so that your institution can continue to receive data because you're maxed out? We can no longer get data into your university because you're saturated. And while users don't really like, at least our users don't seem to really like to pick and choose the data, it's at the point where we joke, you want all the data? You want the whole data feed? You can't handle the feed, man. You can't handle it. And so we're looking at what we've traditionally done as push technologies, where we push data out. We've got to move to more of a pull technology, where users can pull the information they need as they need, as opposed to just give me the whole thing. So for years, we've been exploring server-side technologies that allow you to slice and dice the data remotely and get back what it is you are actually looking to look at.
So you don't need to download a full 20 gigabyte model run if you just want to look at the temperature forecast. Especially if you just want the next 48 hours of temperature forecast, you don't need to download 20 gigabytes of information.
And have you also looked at using something like BitTorrent to ease the distribution load for the sizable data sets that you're dealing with?
So we at Unidata developed a technology called the LDM, the Local Data Manager, which that started back in we'll say mid-90s. I don't have a good handle on the year, but that powers what we call the Internet Data Distribution, which started as a way to distribute so the National Weather Service distributes data to its forecast office across the country using a satellite broadcast. And so one of Unidata's projects was to install a satellite receiver for that. It's called NOAAPort, is the satellite broadcast. And so we have a satellite feed or a satellite dish out there that receives that broadcast, and then we distribute that to universities over the internet using the LDM. And so that's a peer-to-peer transmission software designed to be very quick about, the data there's low latency from when the data arrives here to when it reaches our member institutions. And so we've got this network where, we get it and we distribute to a few top-level nodes. And then those nodes are responsible for, partnering with other, being open to other universities wanting to feed off of it. And so we can have this tree structure of distributing data. It's not exactly BitTorrent, but...
So there was a project called the Next Generation LDM that used the BitTorrent protocol. And what we found is getting universities to open up the firewall for our regular LDM traffic is very tough, but trying to get universities to open the firewall for something that has BitTorrent in the description is pretty much a no-go. Especially a lot of universities are using these turnkey solution firewalls that honestly it doesn't seem like they totally understand. It's kind of black boxish. So even getting internet traffic in on anything other than port 80 is a nightmare. And there have been institutions where they can't get their firewall to accept traffic from the LDM, and they have no choice but to go to a remote server to get data over HTTP instead.
As you guys have mentioned a few times, there's a fair bit of visual modeling and display of the data for being able to interact with it. I'm wondering if there's sort of a inherent need to visualize the data to be able to understand it properly, given the fact of how multidimensional and complex it is from a measurement standpoint, from an analytical standpoint.
Oh, visualizations is the core of what we do in meteorology. I mean, from the time you start as an undergraduate, you spend a lot of time looking at weather maps. And so a lot of what we do is generally looking at these 2D slices. Start at the surface, you're looking at, what we call station model plots. That's taking the various, wind, temperature, dew point, pressure, and plotting it up around the station location in a certain format. And you use that. It's a very dense, information dense format. But once you get used to looking at it, you can really suss out some information. And then, as an undergraduate, and I think, many institutions are still doing that today, you have the students actually do a contour analysis by hand on this data. And so you're drawing into lines of constant value around each of the stations. And it's a very painful exercise, especially when you're first doing it. And you get very familiar with your colored pencils because you got to do temperature in one color and moisture in another color. But what it forces you to do is you really get a handle on what the atmosphere is doing. And you can figure out where fronts are and where the moisture is pulling up, so where you might expect some thunderstorms to fire and things like that. But lots and lots of weather maps. And so doing it at the surface and doing it instead of thinking in terms of height, what we generally do is do maps at constant pressure levels. And so you just work your way up from the surface looking at 850 millibars pressure and 700 and 500 and 300. And so lots of these 2D slices to form a picture of what's going on from the jet stream up at 300 millibars down to what's going on just overhead at maybe 850 and 700 millibars. And then you also have the mid levels at 500 millibars, which really drives a lot of the weather that's taking place. But you get really familiar with looking at a map and seeing the data on it and really making quick judgments of what's going on. It's amazing what the human visual system can do in terms of pattern recognition. You get very quick at, I see that, that's going on. You can also lose it very quickly, as I've learned, but in the height of undergraduate education, you really get good at looking at this. And if you're a forecaster doing this on a daily basis, you get phenomenally good at recognizing these patterns.
And you learn pretty quickly that the human element in all of this is very important. While it's pretty trivial to pass in, say, a gridded field, like a 2D NumPy array of temperature data, and you pass that to Matplotlib's IMShow, and you look at it, or you put it into a contouring routine, you look at the contours, and you go, wow, that's nice and pretty. But when you do it by hand, and you put your knowledge of meteorology into that analysis, you start to see that the computer tools don't always, while the gridding routine is correct and optimal, it's not always truly reflective of what's going on in the atmosphere.
Especially when you consider the noisy observations and, a little bit of instrumentation error, and, you often do with contouring, you're assuming linear interpolation between observations when really atmospherically, really this is kind of bunching up here. So,
for example, if you're looking around a front and if you're contouring, lines of constant pressure, lines of constant height, that they're going to kink around the front. We know from physics that's what's happening. And if we had a dense enough sampling, sure, we would see that, but we don't. So that's some knowledge that you have to put in when you're doing the contours yourself. And you really end up seeing these as pretty much what we're making is an atmospheric topo map. We're mapping out constant heights or constant pressures in the atmosphere and seeing how this fluid flows through these different ridges and valleys, or troughs as we call them in meteorology.
And so there's a lot of 2D planar visualization. You'll also look at cross sections to try and get an idea of a different way to get that three-dimensional picture in your head. There's been a lot of work doing three-dimensional visualization of weather data, and some tools do it better than others. The challenge we face is that's great if you're working interactively with the data, and a lot of people are, but when you need to take snapshots, you want to put it on the web, you want to have it go into a research publication. The 3D visualizations, with some exception, are hard to make stand out without having the interaction, so you can actually get a feel for the depth dimension.
A lot of 3D visualization you see come out of NASA, for example. Those are actually put together in full, almost like animation studios, the same tools that they're using to do movies like Toy Story, and I'm sure I just dated myself a bit there. But it's a full design studio that's putting together these animations and visualizations. And to have a generic general purpose tool to do that, it's just really hard to get something that looks good.
And jumping back down into the code a bit, I was reading through your developer guide and watched the SciPy talk that you gave Ryan about the development automation that you're using for actually creating MetPy. And my understanding from speaking with a number of people who are working in the scientific space and who started in the scientific space is that individuals who do have that kind of background are generally not necessarily as well versed in proper software engineering practices in terms of coding style and test automation and things like that. So I'm curious what your experience has been when interacting with people from that community who are interested in contributing back to MetPy, or at least just understanding the internals of the package.
Well, I should start by saying I really owe my interest in doing these kinds of things to going to SciPy. At some point in my graduate career, I skipped a scientific conference because it was just far away and inconvenient, and instead decided to go, ask my advisor about going to this SciPy conference. This was like 2007, and went and learned a lot and saw a lot of scientifically minded programmers, but trying to do things better, and trying to do things with testing, and trying to do things to make robust software, and not just do some of the things I'd already encountered in graduate school in terms of the research software that runs on one system and doesn't compile on another system. And SciPy really taught me a lot over the years about how to do good software. And so, it was important to me to try to avoid the pitfalls that have befallen many a scientific project, and put in place things to try and keep technical debt from accruing, to not be scared to modify my own library, but that I have if something breaks, it's because my test suite wasn't good enough, and we'll fix that and we'll be better for it, but not be paralyzed to change. And so for contributors coming in, that's definitely something I've worried about. And whenever I get a new one, someone's trying to submit something, I'm very, not cautious, but I'm wondering what's the reaction going to be like when I say, okay, we need to adjust this and this, and can you add a test in this? And so far, those who've been willing to actually just even get to the point of putting in a pull request on GitHub, generally they're very receptive to it, because the people who submit a pull request on GitHub are already a certain level of programmer, either a scientist who's learned Git and is curious about programming at that level, or just a general programmer is used to it and making a contribution. But they've been receptive and going through the steps and eager to learn. And there's usually some hand-holding involved, because not everybody have gone through the 2-year process that it takes to get comfortable with Git and familiar with the pull request model. But generally, with a bit of hand-holding, so far, with a limited number of contributors, admittedly, I haven't had a lot of pushback on that. A few people I just point to, once to the Travis CI runs that we use and say, if you look here, there's a bunch of things being flagged by Flake 8. And thankfully, I haven't had, say, we need to fix this and this. They just saw the errors and kept iterating on it until the errors went away. And so that was great.
So, wonder if each of you could briefly share what are some of the interesting innovations in weather science, either at the research level or at the underlying technology level, as far as sensing and data analysis capabilities go. What are some of the innovations that you're looking forward to that are coming down the pike?
I guess I'll start. I'm excited about this GOES-16 satellite, or as we used to call it, GOES-R, with the different channels that are going to be available to try and retrieve things like how much ice is up there in the clouds, or different cloud types, or things going on at the surface. I'm excited to see that combined with what really excites me is the temporal resolution. So historically, we're used to seeing a full disk of the globe every half hour, or getting images every 5 minutes. Now they're talking about regularly getting images every minute, and potentially for certain special areas where severe weather is going on, or other significant weather, and getting even higher resolution. And so that's just really exciting to finally have a broad coverage of this high temporal information to really see what's going on. It's amazing. If you've ever seen a time lapse of what's going on in the atmosphere, when you speed up some of these processes, you can really see how the air is a fluid, and how you get these wave-like motions, and how a thunderstorm isn't just this big cloud sitting here, but you can see how parts of it are rising and reach out the top of the thunderstorm and kind of descend afterwards. You can just get a better handle on how this fluid really flows. And so it's really cool to see those. And so having 1 minute satellite imagery is really going to help play a role, just seeing the processes going on without needing to fill in with your mind's eye.
Yeah, if you search Twitter for the GOES-16, GOES-16 hashtag, there have been a few pieces of data that have come out from the GOES platform that people are now starting to throw up visualizations of, and it's the reaction on Twitter has been quite amazing to it. I mean, we've got a scene from the TV show back in the 90s, Saved by the Bell, where Jesse's saying, "I'm so excited." I mean, people are totally geeking out over this, and it's great. It is awesome.
We should also say that the weather community has been waiting for this moment for a while. The GOES satellite, this newest one, has been delayed on multiple occasions. And so I think this is at least probably 15 years in the making. I think I remember seeing some articles that were talking about what would be on this thing. And I think it's been another, probably overshot by at least 5 years in terms of when it's finally made space. So we've been kind of waiting for this exciting new data source to go online. And so literally today, we've finally seen some images coming back from the satellite. It launched in November, and they've been doing various checkouts. And so that's in the observational side of things, which I think all of us sitting around the table, we're prone to be more observationalists rather than numerical modelers. And so seeing new observational capabilities is really exciting.
Yeah, I would piggyback off Ryan and say GOES 16 is really what's got me excited. At Unidata, I do data infrastructure in terms of data transport across the network, and dealing with the volume of data that we're going to have from this platform has me really excited, because slicing and dicing the data sets are going to be critical, but also being able to interrogate them remotely in terms of, I want this time to this time, and I want to see this variable, and the imagery is one thing. But then on the server side where the data actually live, trying to aggregate these huge collections of data into some logical data set that can be interrogated in an efficient manner is going to pose quite a challenge. And so that's got my computer programming side pretty excited about the future here.
All right, and I guess I'll go in a similar direction, but maybe a little bit closer to home, not out in space, and say that I'm excited about seeing these highly portable sensor arrays that we can take to interesting events, supercell thunderstorms, tropical events, what have you, and deploy them to get high resolution measurements that maybe are even moving, in the atmosphere like a weather balloon, as opposed to stations that are staying stationary. So seeing what kinds of new data we can collect from events to better understand them as sensors get smaller and cheaper and practically disposable.
And circling back around, what's really exciting about this is, the potential for trying to innovate in the tool space and trying to figure out how we can help out our community of users and make it easier for them to take advantage of these new capabilities by taking off the rough spots in terms of the tools. So making it easier to download these satellite data and do some more advanced things and really help facilitate them doing cool science or just better operational type applications. And so that's what really makes working on something like MetPy exciting.
Yeah, being able to do exploratory data analysis shouldn't be a huge stumbling block that takes weeks to months of labor for a researcher.
So my vision is to have everyone opening up Jupyter notebooks and downloading the data in a few lines of Python and making some cool pictures without needing these huge cells of code. And so that's really how we're looking at trying to approach these problems, is prototype something and look at, okay, that took way too many lines, and let's see how we can take that and make it a generic tool that we can, maybe the tool being a function or a class or something in Python, but trying to, abstract that away and make it so our users can just do it in a few lines and don't have to understand the chain of calls they need to make here.
It's definitely difficult to try and distill the vastness that is meteorology and atmospheric sciences to a podcast that lasts about an hour. But are there any other topics or questions that you think we should cover before we start to close out the show?
No, I think we've hit it. We spent a lot of time talking about meteorology and stuff, but clearly we're all passionate about this field, and it's really the best part about what we get to do is we take our passion for meteorology and put it into tools, especially in a great language like Python. We get to do that every day and work on things to make other people's lives easier. So that's what drives us, and that's what makes it easy to get up in the morning.
Well, I'll ask each of you to send me your preferred contact information so I can put that in the show notes. And with that, I'll bring us to the picks. My pick today is a new podcast that I just came across recently called the Drill to Detail podcast. It's a show that has episodes about data warehousing and big data analysis and some of the different tools and trends going on there. In particular, one of the episodes I listened to recently was really interesting, discussing the idea of data capital. So I'll add a link to that particular show as well. But it's been pretty interesting. I think about half a dozen episodes into it so far, and it's been keeping my interest. So if anybody's interested in hearing about that space, I definitely recommend checking it out. And with that, I'll pass it to you. Do you have any picks for us today, Ryan?
So the one thing I'd like to point out is, so for PyTest, the Python testing framework, there's a plugin called PyTest-MPL. And so that's a plugin that allows you to do image-based tests if you have some matplotlib-based plots that you'd like to test to make sure they keep going. So it makes it very easy to generate a set of baseline images for a test, and then you use that plugin to run your tests, and it can make sure that your images haven't changed. Now, often there's a lot of small changes that can take place that aren't significant, so you can set a certain threshold of difference before the test actually fails. And so, we use that extensively in MetPy to, make sure our plots aren't breaking. And so just anyone out there doing matplotlib-based plots and would like to actually test them, PyTest-MPL makes it a lot easier.
Sean, do you have any picks?
The kids and wife and I watch Trolls, and I wouldn't necessarily give that a pick. How about that?
I watched it myself, and I can relate. It was definitely entertaining and humorous, and there are parts of it where you're just like, I can't believe I'm actually watching this.
Yeah, it was a good one-time thing. I'll leave it at that.
It's a good movie for some family fun. John, do you have any picks for us?
Sure. If you like really technical code-based podcast, I would say check out the embedded.fm podcast. They talk a lot about hardware and making embedded systems, but there's always some really great technical discussions. The episode on Misra C is a good one to start with if you're into that kind of thing. It's just a really enjoyable podcast to listen to every week. So check out embedded.fm.
And I believe that at least some, if not all of you, are involved in another podcast as well. So I'll give you guys the chance to describe that briefly for our listeners who might be interested in checking it out.
Oh, sure. So I actually co-produce a podcast with a faculty member at the University of Oklahoma every week called the Don't Panic Geocast, where we talk about geoscience. So sometimes it's meteorology, sometimes it's geology, sometimes even a little bit more geography. We do interviews. So just a very generalized podcast on the planet that we live on. And it's don'tpanicgeocast.com.
Well, I really appreciate all of you taking the time out of your day to share your work with MetPy and your passion for meteorology. It's definitely been a really interesting conversation, and I learned a lot about what goes on behind the scenes of the daily weather forecast. So I'm happy you were able to join me, and I hope you guys enjoy the rest of your evenings.
Thanks a lot. Happy to be on here.
Thank you.